All right, so welcome to our Environmental Statistics Week 2021. So we're all very excited about this. And today we are very honored to have Professor Howard Chang as our speaker. Howard is a professor in the Department of Biostatistics and Bioinformatics at Emory University, also jointly appointed in the Department of Environmental Health. Howard's primary research interest is in the development and application of statistical methods for analyzing complex spatial, temporal, exposure, and health data. Their current projects focus on two broad areas of population health. One is on exposure assessment for air quality and extreme weather events, especially under a changing climate. And two is on health effect estimation and impact assessment, leveraging large databases such as the birth death certificates, hospital billing records, and the EHR data. So Professor Chang has done tons of impactful work related to environmental health sciences. I'm really looking forward to today's talk. Without further ado, let's welcome Professor Chang.
Thank you, Liu, for the amazing introduction and the organizer for putting this together. And for all of you who are joining us and decided to spend your lunch hour on Monday with me. So I thought today I would share with you some of the work we have been doing, looking at estimating associations between adverse birth outcomes and time-varying environmental exposures. So I probably don't have to say too much about the importance of understanding the causes of adverse birth outcomes. It's been well demonstrated that shorter pregnancy duration is a major cause of neonatal and longer-term morbidity and mortality. And many health studies have been conducted in different regions of the world to look at associations between various environmental exposure and adverse birth outcomes. Our work have mostly been looking at ambient air pollution that will include different air pollutants and their sources, as well as ambient temperature. For large population-based studies, one common approach is to leverage databases of birth certificates, or more recently, electronic health records as well. So this is really one of the reasons why many studies are being conducted throughout the world. And using these large databases have several advantages. I mean, the most obvious one is that often we can achieve very large sample size because these data are routinely collected. It provides great spatial temporal coverage. And we also get a lot of detailed information on maternal and pregnancy characteristics, including often maternal residential address that can be used to link to various environmental exposures. So I was told that I only have 30 minutes today, and the audience is really broad. So I thought today I will focus on just a few things related to birth outcome studies. I want to first talk about a little bit on study design issues for outcomes related to pregnancy length. I'm going to hopefully convince you that various biases may creep in when doing these kind of studies. Then I'll talk a little bit about some of the methods we've been working on for identifying critical exposure windows during pregnancy and their association with birth and birth outcomes. And if I have time in the end, I'll talk some of the other analytic issues that keep me up at night and are fun to work on. So I'm hoping is that some of the topics I discuss will be of interest to many of you. You'll find something that you enjoy. But before we jump into kind of looking at just birth outcome studies, I'd like to kind of frame it in the context of the much broader literature of air pollution and temperature studies. So I call it kind of the traditional studies for mortality and morbidity. So for those of us who works in air pollution or temperature, we often divide the various questions into either short-term exposures or long-term exposures. Short-term exposure are acute effects that might be up to 7 days, whereas long-term exposures are often on the annual level or longer. And because of these different interests in exposure duration, we often utilize different data sources and different study designs and regression modeling, of course. For example, for short-term effects, we often leverage very large administrative databases like insurance claims or the Medicare databases that allows us to assess a very small effect using things like time series or case crossover designs. For long-term exposure, we often leverage prospective cohort studies and look at incidence of CVD or diabetes or mortality. So because of these different exposure of interest and different data sources, often we think very carefully about how to minimize bias. For example, for short-term effects, often we will only leverage the temporal exposure contrast only, versus for long-term exposure, we focus on spatial contrast for our kind of space-time variant exposures. What makes birth outcome studies interesting is that in my mind, they kind of fall right in the middle, where we're often interested in both short-term exposures, whether an acute extreme heat lead to triggers a preterm birth, as well as longer-term exposure, looking at exposure over the entire pregnancy or over a specific trimester. The data that we get are in some way administrative because they're birth certificates, but they also contain information on maternal characteristics. So it kind of also falls in between the administrative versus cohort study. But another important aspect of birth outcome study is that because of the availability of the birth date and maternal address, often the contrast we're interested in are spatial and temporal to examine association. So that really is a lot of interesting statistical challenges we face when doing these kind of analyses. So I thought I would, before I jump into all the kind of interesting things, I do want to say that many of the ideas, methods, and case studies you will see today, they are part of an ongoing NIEHS project, a multi-city, multi-state studies looking at air pollution, extreme heat, and birth outcomes. And Lindsay Darrow at University of Nevada, Reno, and are co-leading this project. And you can see that the project is very interdisciplinary, includes Matt Strickland, an epidemiologist, statistician Josh Warren. We have a meteorologist, Andy Newman at NCAR, as well as air quality exposure assessment using both numerical models and satellite. So, I want to acknowledge these collaborators early on, as well as the many trainees that are involved in this work. Okay, so start with the little cartoons, just to illustrate the kind of the importance of thinking about temporal variation in exposures. So this is a small example. So let's say we're interested in looking at exposure during the third trimester and its association with a preterm birth. So what you see here is in gray is a 7-day moving average or PN 2.5 in my zip code over a particular year. And if we think that there is a pregnancy that ended preterm, and our exposure of interest is the third trimester, typically defined as the period from week 27 to birth. So it's this little average window that we're calling the exposure. One way to do this is to treat the preterm birth as a binary outcome. So a naive approach will be to do a logistic regression or log binomial model, where we'll compare the preterm birth to, let's say, another full-term birth. Here they kind of conceive on the same day, and then looking at their third trimester exposure. But in this case, you will see that just by the definition itself, the third trimester exposure will actually include a period that's after the week 37. Where the preterm birth is defined. So essentially, you are including in your exposure metric a period where the pregnancy is in some way no longer at risk of being preterm. And if you look at, because the seasonality in air pollution that we often see, and it varies by locations, in some way, including this little bit of averaging over a few weeks, it's going to make the exposure lower. Right, so you have the potential to actually induce a positive bias if the mechanistically really is only the third trimester is important for preterm birth. So this is something that is in the kind of more of a cumulative semi-long-term exposure, but the same issues happens if you're working with a more acute exposure, say a 1 week lag, where you might easily define what we mean by a 1 week lag exposure prior to birth for preterm birth. But for full-term birth that has exceeded the 37 completed weeks, it's somewhat conceptually challenging to think about what is the 1 week lag, especially when you have this period that's no longer at risk. Now, you might ask, Howard, does it actually matter? And to understand this bias is more complicated because it's very much dependent on the temporal trend in your exposure and the well-recognized seasonality in conceptions and various birth outcomes. So the one way we can do this is to run a simulation studies where we look at observed air pollution levels. This is in North Carolina, as well as the observed gestational age distribution across time. And we can run a simulation study that looks at what happens if we define these exposures instead of using using something that actually includes when the pregnancy is no longer at risk of being preterm. And the take-home message here really is that for in North Carolina in this period, we will induce a small positive bias. For example, if there really is no association, then if you're looking at long-term entire pregnancy exposure, you're going to have a slight positive bias that increases if the true effect is larger, and similarly for a 4 week lag. Okay, so the take-home message there is that it actually does induce some positive bias. In the other way, so another often kind of design that we see in preterm birth studies is a bidirectional case crossover design. So this really started when we were looking at mortality and hospitalizations. And the idea is to essentially throw out the full-term birth and to really focus on the cases. So in the kind of the most common case crossover design now is done by using a case which is a preterm, and we will identify several control days, usually within the same month, where the preterm did not occur. So, for example, if we have a preterm birth here that's ended on gestational age 36, you might compare this air pollution exposure when the pregnancy was at week 35, week 37, and week 38. So this will be very much a classic implementation of the case crossover design when we look at mortality. Of course, the same issue occurs that if this pregnancy is, a late preterm birth, which is the majority of preterm births, you will also be looking at exposures at a risk period where the pregnancy technically is not at risk of preterm. A potentially even more challenging problem is that when we do a case crossover study, often there is a assumption that the risk is pretty rare and pretty constant across your case control period. So this often will hold for mortality or some of the hospitalizations. But even in our own work, we've seen that this being violated, even for things like asthma, emergency department visit, especially when there's a respiratory infection going on. And so this constant event rate is likely to be violated when you're looking at within a month that the propensity of giving birth will increase sharply over this 1 month period. And in fact, in a more recent simulation studies we did looking at the effect, the potential bias associated with a case crossover study, we actually do see a positive bias. So this is a simulation study looking at daily temperature, looking at short-term 7-day moving average temperature using observed temperature in 50 cities, whether or not there is a temporal trend in conception or there is seasonality in the conception. And the take-home message here is that with the standard implementation of a case crossover design, when there is seasonality in the conceptions, then we actually do detect a positive bias with the case crossover design. This is particularly extreme, or not extreme, but higher in the warm season period. And a lot of the, of course, due to this complex relationship between the temporal trends in exposure and temporal trend in the outcome. So what do we do? So I'll show you two examples that people often will apply to a birth outcome study when they look at preterm birth. One kind of modeling framework that at least our group has been advocating is to really treat gestational length, and this will include things like preterm birth, stillbirth, early birth, as a time to event outcome. And essentially what we do is that we align all the birth records we get by conception date. This is of course estimated based on birth date and gestational weeks. But then once we align every birth by its conception date, we then can think of various time varying exposures, either as a cumulative exposures or as a lag exposure. Another important component of the time to event analysis is to really kind of conceptualize and define what is the at-risk window we are interested in. For preterm birth, for example, we might look at 27 to 36 completed weeks with the understanding that extremely early birth might not be due to environmental exposures like air pollution, but also make a note that all the birth will exit the risk set, let's say when they complete on week 37. Okay, so this will allow us to look at kind of accommodating the fact that the full-term birth is really should be compared to the preterm birth during a very specific period. Something I didn't talk about is this also it's important to remove what's known as a length bias. So once we view this as a time to event outcome, one will realize that the way we ascertain data, often by birth date, means that we will often miss pregnancies that are shorter. And most of the data come to us referenced by birth dates. So we often have to actually exclude all the birth dates in the first year and the last year of our study period to avoid potential length bias. I'm not going to talk about this in detail, but then this reference down here has a nice kind of figure that describes this in detail. But it's a pretty well-known issue in survival analysis. So just to show you how we'll do this analysis. So this is something that is we're just writing these results up, looking at stillbirth and air pollution in Georgia. So we have fetal death records and live birth records between this 8-year period. Maternal address as census tract was linked to bias-corrected CMAC, so air pollutions. And because of the statewide analysis and we want to avoid kind of large-scale spatial confounding, we did analysis within each county running our discrete time survival model and then combine the estimates across the state. But this is a typical result that we'll report for different exposures. You can see how we have a first trimester, a cumulative time varying second trimester exposure, and a cumulative time varying third trimester. The reason why trimester 2 and trimester 3 are time varying because stillbirth is defined as a birth as a fetal death after week 20. So even the second trimester has this kind of cumulative exposure happening. And then we can also look at 1-week lag as well as a 4-week lag. And then total cumulative represents the entire pregnancy duration. So this kind of framework allows us to use the same model to look at different exposure windows of interest. And in this kind of preliminary results we're showing you, we do detect some signal looking at elemental carbon, nitrate during various exposure windows. Okay, so I've talked a little bit, I've talked about various designs. So I thought it might be good to kind of put in a summary, a decision chart of what are some of the things we think about when we start a studies on birth outcomes. Often we start with whether or not the exposure window is different between your cases and controls. If they don't, then a binary regression like a logistic regression is perfectly fine. For example, if you're looking at trimester 1, trimester 2 exposure. If not, then often our default is to do a time to event analysis. But often, or when looking at acute exposure, thinking about many time vary exposures over lots of birth records can become computationally difficult, just simply because you have to construct all the time varying periods. So in that case, if we're working with acute exposures, and if the effect and the exposures are shared, so if you're looking at temperature across the entire city, then often we will resort to a time series analysis where we aggregate the health outcomes. I'm not going to talk a lot about this because there are actually a lot of interesting elements about how do we define the fetuses at risk, and there are two great references down here that if you're interested in this study. But the most of the kind of study that we do these days, because we are able to estimate air pollution and temperature effect, temperature exposure at very fine spatial resolutions now that can be linked to maternal addresses. Often we're working with exposures that we don't want to average over a geographical region and kind of use the exposure directly. So in that case, one of our current favorite is to do a matched case control study. And exactly like what it sounds like, the basic design is that for each preterm case, we'll identify a full-term birth that is at least that the gestational duration is at least our case, and then we'll only compare the exposures during the at-risk window that we're interested in. And of course, the devil's in the detail of how one actually do this matching, because if we match everyone on the same conception date in the same location, obviously they will have the same exposure. So a lot of thinking comes into how do we do this matching to kind of maintain exposure contrast, but also try to avoid confounding as much as possible. So I'll show you one case study, one example that just came out a few months ago, looking at heat waves over the last week and pregnancy duration. This is over 50 US cities over 10 years. So we're analyzing essentially 600,000 preterm births, which makes doing a time varying covariate time to event model challenging. So that's why we resort to a matched case control study. This is a one-to-one match on city, maternal race, and education, looking at weekly lag exposure and whether or not there were extreme heat events during that week. The extreme heat events is defined as a day above the 75th percentile. And you can see that there are various exposure metrics being looked at. The first kind of definition, looking at whether the past week has one extreme day, two extreme days, or three extreme days. Another version of heat waves, whether or not during that week we had 2, 3, or 4 consecutive days that exceeded the 97th percentile. And then finally, a continuous measure, we call the AUC. This is essentially the sum of the exceedance temperature above the 97th percentile. So a lot of details are in this reference. So here we looked at, again, this is a matched case control study looking at early term birth. This is defined 37 to 39 weeks, as well as preterm birth. Overall, you can see how we do see some signals of having an extreme temperature event over the last week trigger early term birth, a little bit weaker for preterm birth, where a signal is only found in the non-Hispanic Black population. So I want to at least kind of show you this study, kind of illustrating this design being used. Okay. So I'm about halfway through, and it looks like I'm right on time. So again, just really the first section, I want to kind of share with you the various study designs that we have used, some of our experiences of why might not work very well because of the seasonality and exposure and conception, and some of the ways that we have addressed that in various case studies. I want to switch gear a little bit, to talk about identifying critical windows. So again, this is a area with lots of people working on it, and various new methods coming out. But the overall theme is that instead of predefining a set of exposure windows, trimester 1, trimester 2, we want to be able to really utilizing the fact that this exposure, like air pollution temperature, is varying over the pregnancy duration. Can we do a better job of estimating and identifying whether there is a critical windows of exposure that might, of course, lead to better understanding of the mechanistic nature of some of the association we're seeing. And again, I'm going to first show you some of the work we've done looking at a time to event outcome for preterm birth. So again, this is just showing the same figure again, but instead of looking at kind of long-term cumulative exposure, we're not going to utilize weekly exposure over the entire pregnancy, comparing a preterm and a full-term birth. And often we are interested in two specific questions in this setup. The first is the critical exposure window. So this asks the question whether or not high exposure that, let's say, occur early during pregnancy is more adverse compared to later pregnancy. They're short term, but we can also ask the questions of a vulnerable outcome window. So what this means is that whether or not ongoing pregnancies are more susceptible to exposure as they progress closer to 37 weeks. So this question is similar to our previous study looking at early term, preterm, whether or not the effect is different based on where the pregnancy is at. So I really do think of these as two different questions. So, and some of these concepts, of course, is also similar to time series model with distributed lag, where we can use polynomial smoother to look at exposure windows. We found that to be challenging to use for several reasons. The first is that first of all, the duration is that we're interested in is pretty constrained. It's from kind of conception till the conception till birth. So this is probably my only equation on this entire slide. But the way we conceptualize this is as follows. So we'll let G index gestational week. So essentially this is the time scale for the time to event model. And then K is the exposure week. So this is a log hazard rate for our model, where we have a baseline hazard that's again indexed by our temporal scale and some confounders that we'll put into the model. But if you look at it right here, so XIK refers to the weekly exposure during week K for individual I. But then the association that we're that we're trying to estimate is not only depend on the week that the exposure happened, but also the timing of that pregnancy. Okay, so to kind of write this out better, essentially the previous time to event model, we have about 315 weekly air pollution effect, which you can kind of stack it nicely in a table like this. Essentially, each of the association has a specific meaning. So for example, this theta 36.1, it means the association of exposure during week 1 and whether or not a preterm will occur on week 36. Okay, so similarly, the other extreme end is whether or not the exposure at week 27 resulted in a higher risk of being born at week 27. So essentially, it's looking at the interaction between all the previous exposure weeks as well as where you are at pregnancy. And of course, you have this staircase staircase structure because you only have 36 weeks of exposure when you are at gestational week 36. So the statistical challenge here is to make sure we can estimate all these associations by borrowing information both across gestational week and across the at-risk outcome windows. And we do this through a Gaussian process, which essentially means that all these data are assumed to be a big normal distribution, and a lot of details are how we actually construct these covariance matrices so we can borrow information essentially more strongly across a risk window and differently across exposure weeks. Okay, so we've cranked our Bayesian machinery and it runs for some time. We run, and we run simulation to make sure the code works. But essentially, this is, some results we might get from this kind of analyses. So what you're seeing here is the weekly association with outcome at different gestational week. So here is a pregnancy that's at week 36, and that's the association of all the past historical weekly exposure. So you can see how for every week, we will have different kind of exposure associations, and they're kind of smooth kind of across the 2 dimensions. This is studied with 5 county Atlanta with TN 2.5. This analysis is a little more complicated because we also control for spatially variant baseline hazard and conception date. But overall, by looking at this, you will see that there seems to be something interesting happening during the second trimester, especially for the earlier gestational weeks for the pregnancies. Now, one great advantage of doing things at the weekly scale from the very beginning is that it then allows me to construct the standard exposure windows that one might be interested in. So for example, if we're interested in trimester 1, we might sum up all of the first 13 weekly effects, assuming that every week increased by 1 unit in exposure. And that allows us to kind of summarize these plots into something that's more familiar to something to kind of and compare to other published studies. So what you're seeing here again is now summarizing the various exposure metrics, pregnancy-wide cumulative exposure by trimester on the first 4 weeks and a 4-week lag, but looking at the association at different outcome windows. So kind of here you can kind of really see how the increased risk being detected when the pregnancy is early on. And in fact, we can further summarize this by summing up across outcome weeks. For example, you can come up with an overall summary, let's say for trimester 1, focusing on just the gestational weeks from 27 to 31. So this is often referred to as early preterm birth, and come up with an overall summarized relative risk and a posterior interval. Okay, so I really like this approach. It really gives you the flexibility to kind of examine the various windows of interest. So again, just to kind of make the point even, so the take-home message is that really we only fit the one model, this model with an individual weekly effect. So we don't have to do a lot of models comparison by fitting one exposure window at a time. So I'm not a big fan of a model selection using things like AIC. They're mostly for prediction. And we've also found in simulation studies that doing these kind of weekly exposure analysis versus pre-averaging things over a trimester increase statistical power. And I also think that gives you a little bit more interpretation complexity. I do want to show that a alternative analysis that if we don't consider the at-risk outcome timing, so if it just if we lump all the outcome weeks together, then you actually will, in fact, in this case study, model the signal quite a bit. In fact, you will still see this increase during the second trimester, but you will not be able to kind of detect this peak during the earlier gestational weeks. Okay. So this is where we started, and since then we have kind of extended this in various ways. So one challenge with using Gaussian process is that it often will over smooth. Even though we run simulation that when there are error, we can still pick up the windows often, but it does tend to over smooth if there really is a very clear window mechanistically. And it doesn't provide a probabilistic measure for us to identify a true window. So one extension that we have done is to kind of add in a variable selection component in these time varying dynamic effects. And we do realize that we have to make them to be correlated. So they're both correlated, they're both Gaussian processes, but they're correlated such that when the magnitude of the effect is high, it has a higher chance of being included into the model. So here's a case studies looking at weekly ozone levels. So this is actually a logistic regression analysis. So this is not a time to event analysis. And that's why when we're looking at preterm birth, everything is restricted only up to week 27. So we don't have this issue with births exiting the risk set. And so, okay, and what you're seeing here is this study in North Carolina, where part of the gamma provides some probabilistic measure of whether or not this week should be included as part of the critical window. And you can see how this that corresponds to this particular window from week probably 5, 4 to 13. And that's the corresponding association being estimated. So again, this extension allows us to kind of have some probabilistic measure of whether or not that critical window is there. And simulation studies also show that by building in this variable selection in the model does help with estimation. Another extension that just happened, so this should coming up soon in the annual supply statistics, but I think the archive manuscript is online. So if you're interested in diving in more, is to kind of add in another component of mixture. So essentially we extend the model such that now the pollutants that we're interested in is both indexed by pregnancy I, week K, but also looking at multiple J many pollutants. So our interest particularly in the chemical constituents of PM2.5 and various gases. And the twist here is that we construct essentially a weighted mixture score where each of the components is weighted by this lambda that sums up to 1. And the lambda itself, you can see how it's also time varying. So not only are we trying to find a critical window, but the composition of this mixture is actually also going to change in time. And again, and these components are all kind of correlated with each other through a Gaussian process. And these are allowed to be 0 through a Gaussian process thresholding. I'm not going to talk about a lot of details because you can find a lot more math in these papers. Okay, looks like I only have a few minutes left, so I think I'm going to wrap up. So I wanted to show you 2 things that I'm excited about in this kind of analysis. But another thing that I've been really interested in is this issue with gestational age uncertainty. So because we're doing a time to event outcome where we align everything by conception date, error in conception date is going to lead to problem with outcome misclassification. It's going to impact exposure because I'm trying to look at trimester 1, trimester 2, and lack exposure. And when we utilize birth certificates data, unlike a prospective birth cohort, which has very stringent protocol, we are relying on what's being reported. Most birth certificate data will report 2 estimates, clinical estimate, or one that's based on last menstrual period, the LMP estimate. Sometimes there'll be a third one that the data custodian feel like it's the best one. Often it's a combination of the 2. And when we look into the actual concordance between them, they can be quite different. For our analysis in Georgia, only about, if you look at clinical versus LMP, only about 62% concordance in defining preterm birth. So this is something that we're very interested in kind of understanding the impact of gestational age uncertainty in various analyses. At least from a very crude sensitivity analysis that we recently did, is to just look at what happens if you use different definitions. So what you're seeing here is for carbon monoxide, elemental carbon, and NOx. trimester 1, trimester 2 exposure, and the risk of preterm birth in Georgia, using the LMP definition for preterm birth, using the clinical definition, using a more inclusive OR definition or more stringent N definition, and something that we try to impute. The general picture is that the associations are pretty robust based on how we define the outcome, but then you do see some evidence of stronger associations if you use a more stringent definition of preterm birth. Okay, so I will wrap up now. That there are many other things that I'm happy to talk about. Things like impact of exposure measurement error. I started from the very beginning saying that a lot of the birth record study really leverage the spatial and the temporal contrast in exposures. What I mean is a lot of time we're using estimated air pollution from fancier model or machine learning algorithms, and there's a lot of questions about whether or not doing a lot of that temporal and spatial extrapolation of exposures will result in differential measurement errors. Another interesting thing is to think about spatial temporal measure confounding and how do we borrow information from other data sources. Something we're very interested in now, looking at electronic health records. I focus on gestational length as the main outcome, but of course, many studies are looking at a continuous birth weight as the outcome of interest. And along that line, we've been really interested in leveraging things like quantile regression to really understand whether or not there's a part of the birth weight distribution that is most affected by these environmental exposures. I do want to give a shout out that we are hiring a research staff and a postdoc. So if you have interest in any of the things I talked about, both the epidemiology, the health studies, or some of the methods, feel free to contact me. And I think that is my last slide. Thank you all for sticking out with me. I actually haven't been monitoring the Zoom, so I don't know if there are questions. I'm happy to take questions now.
A great talk, Howard.
Yeah.
From the audience? So Howard, when you talk about the model, actually, you have a summation, and then within the summation, you have the exposure from each week, gestational. Yeah. So would they be correlated with each other? And especially when they are closer to each other, the correlation probably is even higher. If there is some issue that could be potentially caused by the strong correlation, and therefore the model is not very stable for the estimation?
Yeah, so they are highly correlated. For most air pollution like PM2.5 and ozone, you might be looking at correlation that's above 0.6 or 0.7. And that's a great question. And it does impact how our model is able to detect the true window. Essentially, the smaller the window, the more difficult it is to identify because of the smoothness. Given a fixed sample size, ideally, if there's enough sample size, we can do a good job. And part of the Gaussian process we use to do the shrinkage is trying to kind of leverage the temporal correlation between them. But yes, it's most definitely an issue. That's why in the simulation studies, we often will look at different hypothesized windows to understand how each methods perform differently. In fact, other than our work, people have been using things like wavelets, so very different ways to kind of capture the windows. Mm-hmm. Yeah.
Yeah. We actually have some other previous work a few years ago. We were using the functional data, so functional model that kind of captured the correlation, and in the meanwhile, because this summation becomes an integral, so that also, because to estimate the coefficient curve itself, we add in some penalty, which is kind of close to the ridge penalty.
That's definitely,
so we have a big,
sure. Yeah, no, that's a great idea. We have not done any kind of functional analysis, thinking of the exposure trajectory, right? How do we summarize that in a way such that, yeah, that's a great question, actually. Yeah, because that's all we often use that for the outcome, right? When you have
exactly.
kind of decompose the various signals, but thinking of that in the exposure end, yeah, that is really interesting.
But Howard, we actually had a big issue when using that because you need to have continuous measurement. So most of the days when you have air pollution or exposure measurement, they are not that continuous. So the sparsity of the measurement itself may potentially.
Yeah. No, that's interesting. I should read up some of the. I'll look up your publication and find it. Oh, I see something. You have your hand up. Do you have a question?
Yeah,
or is it just a hello?
Great to see you. And then, yeah, I really enjoy your presentation and thank you for this excellent and very interesting talk. And so one question I have is that, so when we look at this, the window of susceptibility and many of this time series or case crossover design study rely on distributed lag model to identify this, the window of susceptibility. And then I don't think your approach use that, right? So you look at just each week and then, I didn't fully understand the approach you use versus the typical approach using this the discrete lag model. And so can you explain the difference and also the main reason why we use this discrete lag model is that the trimester specific exposure, so aggregating exposure during that period can lead to bias, right? And they're not able to detect this dynamic, the effects over the each trimester. So I'm wondering, so the difference between your.
So I will first say that for distributed lag models, at least in this world, we often will put in a lot more weeks for birth outcomes. And because they are going to be highly correlated and you're looking at 20 weeks in the past, often we have to constrain it. Right? And the standard approach is to do a polynomial spline, something that kind of smooth it out a little bit. So I would say that our approach to kind of penalize each of them, it's a little bit more flexible than imposing a polynomial splines. Some of the fancier distributed lag models also has this idea, like the methods directly stem from the mortality and the morbidity studies also have the assumption that the effect kind of tapers off the further you go. So that's why some of the polynomials are used, but I don't think that is the a priori hypothesis for our for birth outcome studies. The other thing is for distributed model, like you said, often it's applied to time series or case crossover. But traditionally, those analyses, you don't let the exposures overlap too much with the control days. So that's why I don't know whether or not that will be a problem, right? If you're looking at if your case controls are a week apart, but they have overlapping exposures that go beyond a month. So that I also don't know. We haven't really looked into it. So I would say there are a whole lot of similarities, but there are some of the main differences.
Okay.
But most definitely, we can, I think some of the more recent studies have tried to use, let's say, survival analysis, but they try to put in a distributed lags. And I've seen paper that actually seems to work pretty well. Yeah.
Thank you.
Great question. Thank you.
Yeah.
So Howard, you mentioned about the measurement of exposure. Some of those are shared by the community and some are individualized. So what kind of like mechanism or machine that you guys are using like to make them to be more individualized measurement? Do you have some special instruments?
Well, the answer is no. So most of these studies, we are relying on ambient measurements.
Right.
The typical answer will be that, you know, we do recognize that people move around every day, right? And then there's a difference between indoor air quality and what's being measured outdoor. And that is the source of error that we are not going to be able to address here. But I do think that I think there are a few birth cohort studies that we actually recruited moms that are doing a lot more detailed comparison and exposure assessment with the participant. I think those studies will definitely shed a lot of lights on some of the potential issues. Mm-hmm.
Right.
Yeah, I mean, so the environmental engineers, of course, always give us better and better estimates, you know, at like 1 kilometer, at like 50 meters. And it's always, you know, thinking about how to best leverage it in health studies to maximize the exposure contrast, but try not to incur a lot of measurement error and bias on that. I think I like to think about a lot, but I don't have a great solution and answer for you. Mm-hmm.
No, that's very helpful already. I think, you know, that's potentially a direction that we should all work toward to in the future.
Yeah, there's other interesting issues with the exposure assessment for birth cohorts, especially since we're, like I said, we're interested in spatial temporal contrast a lot more and different exposure windows. Mm-hmm. Yeah, what makes individual sort of difficult is that often we will not be often you will not have continuous measurements over the entire 10 months. So often it's kind of snapshots, right? A 24-hour measurements or a week at their home. So then there's another kind of extrapolation from what we can measure, linking back to specific window during pregnancy or the actual personal exposures. Yeah, but you guys are many experts that know a lot more than me.
Awesome.
Yeah.
All right, it's close to 12:55, so I think it's a wonderful talk, and thank you all very much for coming, and thank you, Howard, for this great talk.
Yeah, no, thank you. Hope someone gets something out of it. But and you guys know where I am, so I love talking about designs and biases and how to analyze data. So
great, and we hope to have the opportunity to work together with you in the future.
Yeah. Okay, thanks everyone. Have a good week.
You too. Thank you. Bye.